Hello guys, my name's Charlie. I'm pretty new to F#. I mean, just doing it at home, screwing about on and off for a few months, maybe a few weeks or so. So I decided to put together just a bit of a demonstration that I was going to give at work, which is just like a very basic introduction to it. So if you haven't come across the language before, then hopefully this will be some use. So essentially, F# was originally a Microsoft research project, but probably started about 15 years ago or so. It's driven by sort of the desire to make a sort of a multi-paradigm but sort of functional first programming language. So the whole style and design of the language takes a lot of its influence from like OCaml, ML sort of families, but it tries to push you towards pure functional programming whilst also supporting all the same stuff that .NET, sort of normal .NET, C# currently does. So you can do classes, imperative programming, while loops, all that kind of stuff. So probably the first thing you can know about it is that it's relatively quick and easy to declare things. You've sort of got the let keyword, which is probably the most common thing you'll use in the language, which is essentially an immutable binding sort of between a label, so in this case creator, and a value, which is in this case a string. It's probably also worth noting that it is a strongly typed language, so you've got a compiler that will tell you if you do something stupid, but it's got type inference. So in these top three examples, we've basically got a string and then two lists of strings. It's obviously inferring that, that's a string, fine. Alright. So moving on to sort of function declarations, I kind of laboured the point there that you can sort of give things type annotations if you want, or you've got the example below where obviously it's inferred types. So declaring a function is basically the same as declaring a variable, because I guess functions are sort of first class members of the language, so you can pass them around just like in JavaScript or something. The difference is being that you follow it up with your sort of parameters. So here we've got sort of guess what it does, hopefully multiply x and y. And then below here, we've sort of got an example of a multi-line function. So basically, whenever you have a function or branching or anything, it's always kind of like the last value that there is there, for example, is your return type. So if you've got an if statement, you sort of have two final values of that sort, which need to be the same types, etc. And so just below here, with the square, I've got an example of actually calling a function. You call a function simply by using the function name and then having the two parameters or parameter or whatever put after it. Now, kind of quite an important thing to get your head around about F# is that partial application is a very important technique. So if you're not aware what partial application is, basically in sort of functional programming parlance, I suppose, when you call a function, you're saying you say that you're applying the parameters to that function. So just sort of in sort of the case here, how we applied the parameters of k and 6 to this function here. The idea of partial application is that basically you can give the function only some of the parameters that it needs to do the operation. And the result of that is that you actually get back a new function which takes the parameters that you've sort of missed off, as it were, to order to sort of call it. So in this case here, I've basically declared a new function which you can see has type of float to float. And that's basically been made by calling the function multiply, which takes basically two parameters, float, and then gives you back a float. We've only given it one parameter, and that basically constructs a new function. And that's kind of reflected by the way that the type signatures look. So you've basically got this idea that rather than having one big collection of parameters that sort of goes through, and then you get one thing out the other side, it sort of has this chaining idea where you have a float and a float and a float. And I guess you can kind of think of partial application is that if you only give it its first float, the result is basically that. So a new function. But that sort of comes in, it's used a lot especially when you're using the standard library functions and bits and pieces, which hopefully I'll give examples of soon. Also, please make sure you ask questions as we go along. If you don't ask questions, I'll basically just presume that you understand everything and you'll just sort of carry on smashing through things. But okay, so we've sort of got here an example of a recursive function. So maybe not so much in this example, but one of the sort of key ideas of functional programming is that you try and avoid mutating state sort of at all times. The reason behind that is, and I guess sort of the fundamental idea of functional programming is that you want to try and build large programs out of lots of small little pure functions. And a pure function is essentially a function whereby the outputs are only dependent on the inputs. So it doesn't matter what order you call that function in, sort of through the history of using it or whatever. It doesn't change any state inside of itself. The only thing it does is take the things you give it and almost map them directly to outputs. And the sort of advantages of this generally leads you towards programs that are much easier to reason about. So you can basically just look at a function, you look at what it's called, the parameters it takes and what it gives back, and it's it's very easy to sort of know exactly what that function does without having to worry about the order in which you call it with different parameters, if it changes something, etc. So that's kind of an example of how you can write a function that generally, I'm guessing if that's C style code, you would have a loop of some sort and you would be constantly multiplying, changing a value. Quite a trick often used in functional programming is recursion to achieve the same thing, where you basically call the function, the same function that's calling now, but just with slightly changed parameter. I've also got an example there of anonymous functions. So basically the idea that you can create almost just like a lambda statement, just the same as you can in C# if you use link, that kind of thing, and you can move that around, assign it to things sort of as you like. So yeah, I think that makes sense. So then obviously the sort of next part, what's sort of said earlier, we start with nice little pure functions that are easy to sort of make sense of, and then you build them up together to get sort of slightly more complicated interesting programs. And so very basic, first example here, we've got area of circle R goes to multiply by pi, and then you can see here in brackets we've got square R, so probably makes sense. We're basically evaluating what's in the brackets first and then passing that value straight through to multiply by pi. Also easy. But another very commonly technique used in the language is the pipe function. So you'll see here in the second example, we're basically doing exactly the same thing, where the first line, we're basically, square R, but then we're straight away piping that value into another function, which is basically just another way of chaining things together. And if we get to later examples, which hopefully we will, you'll sort of see how you end up sort of building up programs that look like you're declaring sort of data transformation pipelines, where one thing goes to another thing goes to another thing straight away, and it's quite clean and nice. Sort of unlike imperative code, where you're generally almost doing a step-by-step recipe instruction kind of thing.
I'm guessing the fact it's on different lines, or does it mean it executes it, or is it pure?
No, it doesn't so you can do that. It's quite happy with that. You can also do, it's not quite as clear I think, but you can also do sort of that. So pipe function can go either way, it just sort of depends which way the arrow is going, but generally that's quite weird and hard to read. So yeah, so you can do it.
It's scale quite weird.
It's sort of, yeah, a little bit strange. And then sort of below we've got basically exactly the same function above, but using sort of the pipe operator. So something you can sort of spot about this function here is that we're declaring it with an explicit variable R, although we only actually use R once. We use it in the first function and then we don't care about it anymore because we're straight away moving the result onto another thing. So sort of another way that you can basically chain those functions together is to miss off the argument all together and basically use a composition. arrow, which will basically say I want to construct a new function from these two functions, as it were. So it just takes the result of one, passes it straight through to the other. And then sort of at the bottom here, I'll come back to the toString in a sec. At the bottom, I've kind of got an example of that. So we've got the radius of a circle, which is a float, and we want to print the area of that circle to the command line. So we're basically saying, okay, I want you to square it first, which we sort of define up above. Then straight away, I want you to multiply that by pi r squared. Then we're going to pass it to the toString function, and then finally we're going to pass it to the print function. And it's the language has got quite a cool little way of formatting strings. So the sprintf function is basically a string formatting function, whereby the first parameter is kind of a special string that the compiler will actually have a sort of inspect, and from that string it will be able to infer what types you're actually going to pass through into the function to sort of generate your string. So basically this kind of placeholder indicates that our first parameter is going to go here and it's going to be of type float. So if we got rid of A and instead changed it to just another string, we would get a compile error. Yeah, there. Because it's saying, no, there's an F there, you know, it's strongly typed, so it should be a float, which is sort of quite a nice little thing. And then obviously we're using that same functionality down here by saying the area of the circle is that, and it's expecting a string which it gets from the function up above. Make sense? Awesome. Okay. So types. So it's got full support for the normal .NET type system, so like classes. I can't really think of a lot of things it can't do that, like say C# can. I think partial classes it struggles with, and there might be one or two other things, but essentially anything that you kind of want to do in a class, you can. And you'll see that basically the type keyword is used to declare any kind of sort of type. And here we've basically said, okay, I want a class of dog. It can tell it's a class because we've given it a parameter list afterwards, and then this dog class has got one function called bark, where you know, fairly easy. It's also got support for sort of algebraic data types, which is sort of an unnecessarily tough way of basically saying unions and tuples. So a union is kind of like a num in a sense that it's basically a type that could be one of many options. So in this example here, we've got a job type title union that basically has three different ways that you can construct it. You can either have junior, mid, senior kind of thing. So you can represent like a type that's basically a choice of a couple of things. That same sort of union functionality, you can also assign types to each cases. So you can have, here we have a job title API result. So imagine if we were going to make a call to an untrustworthy source like database or something that could fail. And we're basically going to represent in a strongly typed way all of the cases that call can happen. Our first case, which is our OK case, awesome. That's going to be basically like the OK label of that case, but it's going to have, you know, a type of job title. And you can see just below here, we've got an example of how you could construct that. I think unions is kind of probably best to think of each of the different cases as different constructors for the same type, because it does essentially, I think they basically compile to the same types or maybe subtypes of parent types. I don't know. But yes, so you basically construct them by just using the, you know, whatever case is followed by the type. And then we've got two other cases. So we've got invalid requesting of string, HTTP error of in, and you can add as many of these as you like, kind of thing. Next up, we've got records. So a record is quite straightforward. It's like a struct, so it's just a sort of a key value set of values, essentially. So here we've got one which we've called employee. It's got ID, name, date of birth, and a job title from above. An example of how you create it. So records are designed to be, well, they are immutable, so you can't change any of the values after you've assigned it. So the way that you kind of update, you know, a record with some new values, but you get back a new record, is the copy on update sort of syntax, which you can see here. So we're basically saying I want to make a new record based off Bob, but we're going to change Bob's job title to mid. So that's basically, you know, how you can change it without having to mutate existing state. Next up is tuples. So tuple, hopefully you're familiar with them from a lot of other languages. It's basically just an unlabeled set of types. So here we've got a tuple that's basically made up of an int and a string. They use like Python things, and tuples should hopefully be quite familiar. An example of how you would create a tuple. So the compiler will infer, the actual label, the actual type of the tuple just from the arguments that you give it, obviously. So if we try to add something new there, wait, that's not a value, it's a type, like that, we should get a compile error. Or does that just create a new? Oh, that's alright, it's just created a new tuple, but it's a different type. So obviously when we then try to decompose that tuple and assign an x and a y to it, it's throwing an error and saying no, don't like. Alright. Type keyword is quite flexible as well, so you can also create type aliases. So if you've got like maybe relatively complex, generic like library or collection types that you want to basically give a more easier to sort of handle name, you can do that. In that example, we've got a GUID, which is an existing .NET sort of type we're assigning to employee ID. And you can also use those same type aliases to basically create names for certain functions. So the example we've got here is we're basically creating sort of a type that's an employee serializer. So essentially, just a function that takes an employee and gives you back a string. And so I think I've sort of got an example there of sort of creating relatively basic sort of form of that. We've got a JSON serializer, which is an instance of employee serializer, and we've assigned that to an anonymous function that takes an employee and basically breaks it down just using the same sprintf function that we used earlier. And just using things like unions and tuples, you can combine them together and actually represent types in a relatively elegant sort of neat way. I've kind of introduced the option type here just because I think it's used in other slides, and it's used a lot in the library, which is basically a type that is an optional value. So F# by default doesn't have nulls. Wait, I think it does support nulls, obviously, because it's .NET, but if you just write, normal idiomatic .NET code, you won't end up with nulls anywhere. So how the library would represent a value that's optional is using this construct. So you give an option type that's either a none or a case of, some A. Also, that's worth mentioning generic types. So if you're familiar with C#, Java, it looks fairly similar, except they ask you to put this little squiggle in front of it. I don't really understand why. And then, finally, a case of what I was saying before about sort of being able to quite nicely represent, types that maybe in C# might be a bit of a larger class. We've got a binary tree, which you can think of as, either an empty tree, there isn't anything there, or you're going to have a case of a node, which is basically a value. So you can think of that A as like sort of the node value of your sort of small tree, and then you've got a tree on the left of it, which we've got here with the left-hand union case, and a tree on the right of it. So it's kind of this recursive definition where it sort of uses its own name to allow you sort of to collect types, which is quite nice. Moving on to collections. So obviously it's a .NET language, so you can use any collections that you can find in C#. But it's got a few of its own collections that you use quite a lot, just because it's got slightly nicer constructs and way of working with them. The first example is list, which by sort of their implementation you can think of as a linked list. So a linked list, for anyone who doesn't know, is the idea that you basically have a list can basically be broken down into lots of individual sort of cells, all linked together with sort of one pointer that just goes from your current sort of value, which is called the head, like the first value on your list, and then a pointer to sort of the rest of your list, which you sort of see you can construct an empty list like that way, a list of just 2, 3. Going on the idea that I said before, that a linked list is kind of a head and then other values. You sort of use the cons operator, which is this thing to basically construct that. So here we're basically prepending 1, 2 and 3. You can do range stuff, so 4 to 7, relatively self-explanatory, and you can concatenate lists. Basically just got a bunch of operators and things to make working with lists easy, because you do use them a lot when you're writing code. And then finally got an example of like a list generator, I guess. So I think that probably makes sense. Hopefully we're saying for each I in the range of 0 to 100, if it's an even number, then yield. So in example, you see maps. So they have maps which you can basically, sort of self-explanatory, it's like a dictionary, so it maps keys to values. I've not really found a nice way to construct a map yet. So they've got this function which is of list in the map sort of static module, which takes basically, as you can guess, a list of tuples of keys and values and turns it into a list. Fairly dull. And then got an example here of constructing arrays. So arrays you construct basically in exactly the same way as you would a list. So a list is just that, but the difference is that you add bars to like the insides of the brackets. An array, as you'd imagine, it's more efficient. You can change values in place, which is what this is doing here. So if you've got something that you're worried about RAM or it needs to be fast, then sort of a way that you can optimize things. And then finally at the bottom, I've sort of taken the stuff that I've been talking about in the last two slides, so collections and types, and built a JSON serializer. So hopefully, this is an old version of the talk, isn't it? Never mind. So hopefully, let me just set it. Sorry, it just looks a bit different. Anyway, so yeah, going to create like a JSON serializer. So first we kind of need our code representation of a JSON object. And if you think that a JSON value can more or less be three things, I mean, it's a little bit of a lie because, it can be a string, it can be a bool, it can be null, sort of simplified things to basically say that you can either have a JSON value or you can have a JSON array, which in this case we're representing as a list of JSON values, or you can have an object, which is basically just a map of string values to JSON keys. And then I've written this function here which will serialize that to sort of a JSON format. So kind of explain what's going on here. Have I missed pattern matching? I might have missed pattern matching. Okay, I think I've done these slightly in the wrong order. Essentially, to describe to you what pattern matching is, it's an extremely powerful way of doing conditional branching in your code. You can think of it sort of like a switch statement, insofar as that you give it a list of patterns and it will go down to sort of each different pattern, and the first one that matches the object that it's trying to match on, it will go, yep, that's good, I'll execute that. So if you think a slightly more basic version of a pattern match, you can think of so going to create a function that takes the same sort of linked list type that we were using before and tells us if it's empty or not. So we can go match list with okay, so essentially what there's lots of different ways to sort of deconstruct types when you're trying to do a pattern match. So the compiler recognises that when you're using two closed brackets, it's the same thing that you use to create an empty list. And I guess you can kind of think what we're doing here is kind of the opposite. We're taking a completed list object and we're almost trying to guess how it was put together in the first place. So in this case, the first branch would match obviously an empty list with no values, and then for the second branch, we've basically just said anything else is false. And also, the compiler should be able to infer from the fact that that's the constructor for a list that this L is actually a type of list. It's not just a random thing. So it's all sort of strongly typed. So hopefully that's enough of an introduction to pattern matching. So yeah.
Does it force completeness? So you have to match everything in a given.
It warns you. So if we just have the same code, I think you can still compile and run, but you will get squiggles. So yeah, it's going incomplete pattern match on this expression. So you can still run the code. I think if you run that on a non-empty list, it'll probably throw an exception. But I'm pretty sure there's probably a setting somewhere where you can force it to not compile if you miss out all of your cases. So sort of building on that, we're basically going to deconstruct this JSON thing with of this type. The first case is easy. We're going to say if it's a value of v. Which again, if you remember from when we were using tuples, it's exactly the same sort of expression that you would use to create, a tuple of this type. So we're almost just sort of deconstructing and extracting out the value into this v here. So we're going to say, okay, if it's a JSON value, then I want you to extract out the string, which is what it assigns to this v, and I want you to format a string, which is basically just two quotations. It's red, obviously, because it's an escape character. Two quotations either side of the formatted string. It's easy. Next one down, we've got an array of values. So values in this case has basically been taken out and it's been assigned. It said, okay, I know that values is a list of JSON. So if you were to process a list of JSON values, I guess if you were doing it in like a C sort of style, you would just loop through them. Each individual JSON value in the list, you would, see, realize each individual value, and then you would just slam them all together with commas in between and wrap it in square brackets, which is basically what we're doing here. And you can kind of see now how that kind of pipeline style of coding is kind of being used. So we're first function we've essentially got is map from the list sort of module, and we're saying, okay, I want you to map over all of the values and recursively pass them each through, so you get each JSON object back. Then out of that we end up with basically a list of strings. So we format the strings together by concatenating them with a comma, and then eventually wrap them in square brackets, and that's it. Objects quite similar, but obviously rather than just having a list of strings, we actually have a sequence, which is just what seq stands for. So I think it's an alias for I enumerable, if you know C sharp. We have a sequence of key value pairs which we're formatting together in sort of, same way. We've got key there inside some quotations, and then a value which we're also just recursively turning into JSON, and then doing the same thing, putting the string together, turning it to a thing, and that's it. So I think that should be a working example, so I should be able to highlight that. So I've written these in an F# script files. So F# is really good for scripting. A script is basically just a self-contained module, namespace, everything. So you don't need CS prod, you don't need anything. You just have one file and should be able to just do that. And yeah, that's done. So it's got JSON blob there. Okay, awesome. I think that's probably all I probably feel comfortable talking about. There's lots of other random half-complete stuff. Actually, yeah, I'll sort of talk about a few things here. I swear this is an older version of mine.
Charlie, can I ask one question?
Yeah, of course.
In your sort of day job, what would you say is the biggest problem or project that this has really helped you most with?
Yeah, so I mean, we're not actually using F# at where I work yet. I'm trying to fix that. But sort of recently we've been taking on a couple of projects where we're doing more distributed systems, sort of. So basically systems that run across a lot of different boxes. And once we sort of got into doing a lot more of that, you realise that concurrency, managing state and things becomes very, very tough. So I suppose in an object-oriented system where your state and your data are very tightly bound together inside the same process, inside the same class, you now sort of have the case where you're moving data all over a network to different machines that are sort of doing things on it. And if you don't design your program in a certain way, it's very easy to basically shoot yourself in the foot and get race conditions or all sorts of issues that kind of happen when you don't use like sort of functional-esque, well, certainly at least a mutable sort of programming style. So actually, like a lot of our C# code is starting to look like this because we sort of need the ideas to be able to make a functioning sort of message passing system. So yeah, I'm trying to make it a bit easier, ideally by getting this in there. So yeah, I think I did actually have a section on pattern matching that I found, but to be honest, I think we probably, yeah, that's the newer version. We've sort of covered everything there. I think it's just a few more examples. So I've got my empty list example. There's a quick sort example there. I think the equivalent quick sort example in C# maybe might be 10 lines of code, maybe more, twice as much. So it's a really good language for expressing sort of algebraic or some quite algorithm-heavy code. And what you kind of find, because you've got a compiler and a type system that helps you a lot more than it does in C#, and the programming experience is kind of quite different. Insofar as that you don't really find yourself using a debugger that much, maybe for things where you've been really stuck for a while or whatever, but you generally find yourself just fighting the compiler a lot. It's more difficult to get your code to compile because the compiler's doing it's doing a lot more to help you. It's trying to stop you, doing something stupid. So it does take longer to get your code to compile generally when you use this fashion, this kind of style. But the nice thing is that very often, once it compiles, it just sort of works, and you don't really have any issues or exceptions or runtime errors. It just sort of works. Not all the time, that's not a promise, but a lot of the time it works. Okay, I think I'm probably done. I imagine there isn't that much more time left. If we've got a few minutes, yeah, well, I mean, I can do now. I was going to very quickly show you a function that obviously isn't working here because I haven't got an internet connection. So that's what they're called type providers. So type providers it's not a core part of the language, but it just kind of shows you the sort of cool stuff that they're doing with the compiler that you don't see often in a lot of other languages. So a type provider is basically something that provides compile time information to the compiler so that the compiler can give you basically strongly typed queries and requests to sort of remote data sources. So this example, it's all red because I haven't got an internet connection. But basically here I'm using the Swagger provider. So if you don't know what Swagger is, it's basically a JSON standard for representing a REST endpoint. So you can write a Swagger file that represents your endpoint, and then you can generate clients and sort of other bits and pieces. So F# here, if I had an internet connection, well, what the compiler would essentially be doing is at compile time, it'll be going across the internet, finding this Swagger doc, pulling it down, and then passing it, and basically coming up with a strongly typed model of the data and functions that exist on that endpoint. So you've got here like a get user by name, which is something that it generates for you. It generates all the entities for you. It's basically like you sort of get quite a lot of stuff done for you just with this one line of code. And sort of another example of that I've got below is I don't have an SQL one here, but like as I sort of said at the top, there's type providers for SQL, JSON, web services in general, OData. So OData, I don't think it's really used that much, but it's sort of like similar. Like an open platform agnostic sort of way to define like a data query point. Like it could be an SQL database or something else. Again, this won't compile because I haven't got any internet connection. But basically, this will be doing the same thing. It'll be going off to this public northwind.svc thing and basically building up, type information about that endpoint. At which point you can then use link on it. So this is just exactly the same as normal C# link. Or a query expression, which is sort of part of another different part of F# functionality called computational builders that I might try and explain in the next talk. I'm not sure if I really understand them enough. But yeah, guys, that's essentially it. Got any questions or anything?
CSV provider is pretty awesome for F#.
Yeah.
You can basically query a CSV file that will give you all the headers as actual properties, so you can sort of work with CSV files a lot nicer.
Yeah, it's like I really like the SQL one, like for sort of means like you don't necessarily have to try and manage like entity framework, sort of managing the schema in C# and things. You basically just have your database schema, which is your SQL migration scripts and all that stuff, and then you basically get compile time code generation for that schema. It's quite nice, but yeah, it's a cool function.
So, me and my having a C#, it sounds like the benefit of this is that it puts me on Rails and forces me to be functional.
Yes, I mean it doesn't. I wouldn't say it forces you because you can write code. It supports what like while loops, objects, properties. You can still write code very much how you write C# code, but yeah, it definitely sort of pushes you gently towards the style of coding where you're more functional coding. You're leaning on the type system more. I guess so.
It interrupts very nicely with C#, so you don't have to be too functional, where you can kind of take little bits of it and just reference stuff that you use in C#.
If I become a functional guru then, you can just write algorithms, functional Why would I then want let's say a whole chunk of stuff in C#, why would I want to add an F# module to say
Just doing
C#?
Well, I mean, I think like so. I think the sort of stricter type system and the more help the compiler gives you is really good when you're dealing with very complicated domains. So like quite a nice way to use the language is if you're trying to build so we're building a sort of audience-based distributed system at work. It's got quite a complicated domain model expressed in lots of C# classes with lots of boilerplate and all sorts of things. A really good way to interrupt with this would be to use F# just as your pure functional domain modeling, but then still use C# for all the Python infrastructure. Because when it comes to using existing systems, so like ASP.NET or like basically a lot of really well-known .NET tech, they weren't really designed with F# in mind. So you can write ASP.NET code as F#, but it's kind of clunky because you're kind of forced. Not really using the language what it was meant to do. You can do it, but it doesn't really like so a really good way for them to interrupt is to lean on C# so you can use all your existing libraries and things in a way that's nice and doesn't make you want to cry. And then just use F# for like the complicated domain modeling kind of stuff. If you've got algorithms doing relatively difficult stuff and bits and pieces, that kind of way, I guess.
I think it makes it a bit more succinct.
Yeah.
Which is that easy to read.
Yeah. Like it's sort of like one thing I noticed about F# is that once you kind of get used to the language and then you cross over to try to understand like the core libraries, actually how the people who write F# write F#, it's not that much of a jump. Like it's quite easy to understand what they're doing. I think, like as you said, it's sort of more succinct, and the code generally it represents the sort of what the programmer was trying to do, in their head, better than if the programmer, had this idea in their head, then they had to dive down into all these details of how they actually implemented it and stuff. I think because the compiler does a lot of that for you, you spend, less time trying to understand and going, why is this person trying to code this in that way, kind of thing. Alright.
Thanks, Charlie.
No worries.